Hey everyone and welcome back to PrepFusion. I'm Anish and today we'll start the lecture 3A of this electrostatics chapter. So we have finished electric field intensity. I gave you a homework. Let's just show what how I have solved that particular question. Also, we'll start in today's lecture Gauss's law. Okay, we'll understand what electric flux is, what is Gauss law, and we'll do few questions on that. So this lecture is very important. All the lectures are very important here because electrostatic in itself is a small syllabus, so we have to cover everything from it. Okay, before going, right, I will go and start this question 31, right? So I gave you, we have infinite sheets at particular locations and I have to find the electric field intensity at point P1 and P2. Now if I want to find at point P1, right, just the crux of electric field intensity or the force due to charges is you write the magnitude, you write the direction separately. Okay, so here I have a positive charge, okay, positive surface charge density. This is negative, this is positive. So due to this positive charge, the electric field intensity at P1 will be in the minus AZ cap direction. This is the Z axis, minus AZ cap direction. The electric field due to this negative charge surface charge density will be in this direction because field will terminate here. So it will be again minus AZ cap. Due to this negative surface charge density as well, this will be again in the minus AZ cap direction. Okay, I hope you got the point. Now everything is minus AZ cap, but what is the magnitude? Magnitude, if you remember, it's constant. It is sigma upon 2e, basically surface charge density upon the epsilon. Okay, so this has plus sigma, so this will be sigma upon 2e. This has minus 2 sigma, but I will write here 2 sigma only because I will only take the magnitude. Direction has already been taken care of. So that's the summary of whatever we have been learning. Direction you write separately, magnitude you write separately, else you will be confused. You will be confused, trust me. If you learn from other educators, you know how confusing the direction part is. Okay, so you write the magnitude here 2 sigma by 2 epsilon, then sigma by 2 epsilon. That's it for this third sheet. Then if you add all these three, these are in negative AZ direction, so this will be 2 sigma upon epsilon. Okay, so that's the answer of this particular electric field intensity for the first part. Second part is for point P2. What will happen for point P2? In P2, if I observe, due to this positive surface charge density, the electric field direction will be in minus AZ cap direction. Due to this negative, now direction has changed. It is terminating, right? It should always terminate. So it is in the plus AZ cap direction, and due to this negative as well, it is terminating. So it is again in the minus AZ cap direction. So this becomes plus AZ cap due to the second sheet. Due to the third sheet, it becomes minus AZ cap. Okay, so this is terminating here and this is terminating here. So basically what will happen, finally everything will get cancel each other out and electric field intensity will be 0. So between these two sheets, right, between sheets 2 and 3, the electric field intensity throughout the whole region will always be 0. Will always be 0. This acts as a shield. Okay, there is no electric field intensity here. Okay, this acts as a perfect shield. There is no electric field intensity. So if there is some sensitive component that actually can get destroyed due to electric field, I can place it over here. Okay, so that is also an example of electric shielding that I taught you here. Okay, that I taught you here, that is also an example. There is no electric field here. Okay, that is the thing that I was trying to explain in the previous lecture. Now let's start with the electric flux. What is electric flux? Electric flux represents the flow of electric field through a surface / area. It can be thought of as the number of electric field lines passing normally is very important, right? This point I will come to later on, don't worry. Normally through a given area. We can understand this by example of waterfall. Okay, so let's say I have this mountain, right? Then water is falling from this mountain, right? We know waterfalls. Now if I place just a net over here, okay, just a net, so water will pass through this, right? Water will pass through this net. So the amount of water that is passing through this net is the analogous to amount of electric field lines passing through a particular surface or area. Okay, so this is water is analogous to electric flux here. Okay, I hope you understand. This normally part I will come to, don't worry, but perpendicular part I will come to. Now there are two definitions for electric flux. Actually what we learned in our 11th and 12th, we learned that electric flux is equals to electric field intensity E dot A vector. A vector, surface vector, I have already taught you. Okay, surface vector has already been taught. Don't ask me what is surface vector. Okay, don't ask me that. Next, this is electric field intensity. There is a new term in engineering, what we learn is D dot A. Now D dot A is nothing but the same thing only. D is basically the electric flux density. This thing is known as the electric flux density. This is electric flux density. Now you might ask, sir, why are there two definitions? So in physics, right, we actually don't use this concept. Like, we are not using it in our daily lives, right? We are not using electric field concept, all those things in our daily lives. In engineering, we are actually using this flux concept in our daily lives. We are making machines, we are making components. So here what happens is that I have D. It is easier for me to do the computations with D and rather than with E. That's why I use. So easy use, for easy use. Engineers find a way out, okay? They find which one is easier for me to use. That one I will use. So this one makes the calculations simpler. Makes calculations simpler. I will explain why. I will explain it why, okay? So this is about D dot A, but exactly what is flux? So here if I have a sheet of paper, let's say this is a sheet of paper, right? This is a sheet of paper and some flux will pass through this. Now, what is the total flux that is passing through this? What is the total flux that is passing through this? It actually depends on multiple things. First of all, flux actually obviously depends on the area of the surface through which the electric field lines are getting passed. Flux actually obviously depends on the electric field intensity. Obviously, if there are more lines, like see, here are 4 lines, here are 3 lines. So here there will be less flux, here there will be more flux. So it depends on the electric field intensity, and it depends on the area of the surface. If the area is bigger, right, more it can pass in more flux because more lines will cross. The more number of lines that crosses through the surface, the more flux I have. Okay. Now, if I place this sheet tilted, a bit, then what will happen? The interesting fact is actually the number of lines will pass lower, because here, right, during the H case, these lines will not pass. If this was in straight line, these lines would have passed. So what is wrong here? What is different here? The difference is it actually depends on the angle that I am placing the surface with respect to the field lines. It actually depends. Flux actually is a function of the angle that I am placing with respect to the electric field lines. Now, if it is in the same angle, right, with the electric field lines, no electric field lines crosses. It is just parallel. This is my sheet, okay, and my flux direction is like this, okay, parallel to this. So it will be parallel, basically no field lines are crossing. But if it is like this, right, if it is like this, or if it is like this, just coming out of the screen or coming inside the screen, what will happen? Field lines will actually pass through this. So basically, if angle is 90, then I get full electric field lines, that is flux becomes maximum. If angle is 0, flux is 0. Okay, so that's why, which gives angle 90 maximum cos. So that's why there will be a cos component. That's why it is D dot A, or if I break this down, this will be D A cos theta. Okay, so it depends on cos theta. Okay, so that's why flux depends on all this. We'll expand on this later on, don't worry. Just to give you the visualization, how does flux depend? Let's start. What is electric flux density? Electric flux density represents the number of electric field lines crossing per unit area. If I divide this by area, right, this will be my electric flux density. So basically, it has another unit. Electric flux density has another relation, that is electric flux density is epsilon E. Okay, it is independent of medium, because medium is already been taken care of. Okay, so we use this D because the flux that will like the D in vacuum and the D in some other, let's say water medium, will be same. D in vacuum, D in water will be same, because already internally the formula for epsilon is taken care of. So it is easier, I will say D vacuum and D water is same. So it is easier for me to just write a single number, because every time I will change my atmosphere, I have to change this E as well, right? Epsilon will change, okay, but here it will not change, right? So it's easier for engineers to do the computation, so that's why we use D and not E. Okay, so D has this formula, E is this, right, for a point charge, and D will be just independent of epsilon, because if I multiply epsilon with this, epsilon will get cancelled and it will be Q by 4 pi r square. It will be independent of epsilon. Okay, I hope you got the point. Now let's do a basic question on flux density, right? Let's do a basic question on flux density to get more of the feel of flux density. Find the flux density at a point A equals to 6, 4, minus 5 caused by the following. So if I have a point charge located at the origin, find the flux density. So we'll mark the axis. This will be point charge. Okay, so find the flux density at a point 6, A, 4. So 6 will be somewhere here, 4 will be somewhere, 6 will be somewhere here, 4 will be here, and minus 5 will be here. It will be somewhere here, right? So basically I have to find the flux density, because due to this point charge, right, this point charge is, let's name this as Q, it will actually generate field everywhere. Okay, and at this point I just have to find the distance. So what will be the distance? Basically this P, what will be the distance? OP vector, it will be simply 6, like first of all I will write what is my OP vector, distance from the point charge. It is 6AX cap plus 4AY cap minus 5AZ cap. Correct. So magnitude of OP vector will be 36 plus 16 plus 25 whole under root. Okay, so it will be some value. I will just quickly write it down, just hold on. It is 52 plus 25, that is 77, I think. So 36 plus 16 plus 25 is 77 under root 77. Okay, now what we will do, I will just simply use this formula. What is electric flux density due to a point charge formula? Simple, just epsilon will not be there, it will be 4 pi r square, Q upon 4 pi r square, right? So Q is how much? Q is 20 millicoulomb minus 3 divided by 4 pi into r square will be 77. So it will be in some millicoulombs. Obviously I have to write the vector format as well, right? AR cap, because it will be radially outward through this point, so it will be this divided by its own magnitude. So copy this, divide by its own magnitude. So this will be the electric flux density. Okay, this will be the electric flux density for this particular question. Okay, and one more thing, the unit of electric flux density I forgot to mention, it is in coulomb per meter square. Okay, the SI unit of electric flux density is coulomb per meter square. Now here this will be in like this is 10 raised to the minus 3. If I just don't write 10 raised to the minus 3, as it doesn't look good, millicoulomb per meter square. So that will be the unit of electric flux density. Now let us do other question, right? Let us do like the part B. This was the part A. If I do the part B, a uniform line charge rho L equals to this on the Z axis. So again I will copy, I will write the Z axis, right, on the Z axis. Okay, so it is an infinite line charge, it is an infinite line charge x, y, and I am lying somewhere around on the negative. So this is actually point A, whatever, it doesn't matter, I will just write this point P because it's suitable that way. Okay, because I have just chosen point P. So P will be somewhere around, it's in the negative x, right? No, it's in the positive x. P will be somewhere around here. Okay, so how do I know? So again this direction will be, it's in the Z direction, right? So this will be radially outward, right? Everywhere radially outward. So here this will have, basically this will not have the Z component. The Z component will be hidden from this because this is in the z axis itself. So what will be the direction of the electric field? It will be the arrow direction, arrow cap. Okay, always remember, due to a line charge we choose a cylindrical coordinate system, and in cylindrical coordinate system what will happen is that direction will be just radially outward from this. We will assume that this is the midpoint. This is the midpoint. So from the midpoint, if you remember, it was 2k lambda by 2k lambda by r. Okay, if you remember, it was 2k lambda by r. So r naught. So here what will happen is that arrow cap will be what? Arrow cap will be what? This direction will be what? So what is this point actually? This is the midpoint. This is the, again, this is the foot of the perpendicular. Okay, so what is this point? This point will be just same, x and y coordinates will be same. Z coordinate, sorry, I mean z coordinate will be same, x and y coordinate will be what? 0, 0. So this will be 0, 0, because this is passing through the origin itself. This is the z axis itself. Just z component will be same. Z component will be what? Whatever the z component here was. Z component here was what? -5. So this will be -5. Okay, this is the foot of the perpendicular. I hope you understand. This I will assume is the midpoint, symmetric case, right? So arrow cap will be just 6 minus 0 ax cap plus 4 minus 0 ay cap plus -5 minus 5 az cap. Okay, so obviously I have to divide by magnitude as well. This will be 36 plus 4 16 52. 36 plus 4 15, yeah, it will be 52. Okay, so magnitude will be 52 simply. So now I know arrow cap direction, I know the magnitude. What was the magnitude? If you remember, due to a line charge the electric field intensity was, okay, due to line charge the electric field intensity E perpendicular was, magnitude I am talking about, direction I have already found out, 2k lambda by r naught, right? So if I want to reduce this in epsilon format, this will be 1 by 4 pi epsilon, so 2 pi epsilon r naught. Okay, this was the reduced format. Now here I have to multiply epsilon as well, so my d perpendicular magnitude will be just independent of epsilon, so it will be 2 pi r naught. R naught is what? R naught is this distance, right? R naught is basically this distance. That is the distance between this and foot of the perpendicular and the point P. So d net will be lambda. They have given us, yes, they have given us lambda 20 microcoulomb per meter. So I will just write this in micro itself. 20 divided by 2 pi into r naught is 152 into the direction arrow cap. Arrow cap is what? Arrow cap is 6 as cap plus 4 ay cap divided by, again, the division of this is, that is 152, as this is a unit vector. Okay, in microcoulomb per meter. Okay, meter square, microcoulomb per meter square. So this will be the solution to this particular question. I hope you like got the understood the points, the solution of this. Let's go back to the third one, C part. So in the C part I have a uniform surface charge density rho s on the plane x equals to 8. X equals to 8 means it lies on the plane yz. Okay, so we'll solve this in the next page. So again, if I draw the coordinate axis, xyz, okay, and it lies on the plane x equals to 8, that means yz plane. X equal to 8 is somewhere around here. So and it is like terminating at infinity, and my point is somewhere around here, right? This is my point. It is at 1 comma 6 comma 4 comma minus 5, 6 comma 4 comma minus 5. Okay, now this, right, this is again infinity, so this is again symmetrical case. This will either provide electric field intensity here or here. Is it positive or negative? It is positive. Let's take a good case. Let's take it as negative. Okay, for better understanding, let's take it negative. Now if I choose this as negative, okay, this negative is very small, that isn't going to cut it for us. Yeah, this negative is good. So if I choose this as a negative, right, so basically this has negative charge density, surface charge density. So obviously the electric field intensity or the flux density will have same direction only, just epsilon is not there, will be in this direction, right? It will be terminating at the surface because it is towards the origin. Okay, this is more away from the origin, this is more on the behind the point, so this will terminate, right? Because this is exact plane at x equals to what? X equals to, this is at x equals to 8 and this is what? X equals to 6, correct? So if this is at x equals to 6 and this is at x equals to 8, simply it will always be terminating here. This will always be terminating here. So this surface is very simple to understand, right? This surface is very simple to understand. Okay, so there as well in the previous equation which I did with the surface charge, you have to understand where my point is lying with respect to the surface, behind or in front of the origin. It is very important for you to understand that. So again, this will be in what direction? Perpendicular to this surface. What is perpendicular to this surface? What is perpendicular to the surface? X equals to 8 means YZ plane. YZ planes means either plus minus AX cap. So basically the direction, my electric flux density will be plus minus AX cap, but at point P the direction will be only minus because I am more towards origin. It will be minus AX cap. Okay, so that direction has been taken care of. What about the okay, sorry, this is terminating here, right? Sorry, this is not positive charge, this is negative charge, so direction will be plus. This is terminating, right? This is negative charge, so direction will be plus. What about the magnitude? Magnitude of the electric flux density will be simply, we have just derived, it is sigma upon 2 epsilon for electric field intensity, right? So it will be sigma upon 2. Am I correct? It will be simply sigma upon 2. Just if I want to write it, if I remember, for electric field intensity we just derived in the previous lecture, it was sigma upon 2e. So it will be sigma upon 2. So if it is sigma upon 2, things will be pretty simple. So now I will write my electric flux density. It will be sigma is how much? Minus, I will not write the minus because minus has already been taken care of. I will just directly write 60 microfarad. So 60 micro is already there. 60 by 2 is 30 micro. And the direction is plus AX cap. Okay, this will be pretty simple actually, microcoulomb per meter square. So this will be the answer for this particular question. Okay, 30 microcoulomb per meter square. So this was pretty simple. I hope you got the feel of electric field flux density. Electric flux density. This is not electric field intensity, it is electric flux density. Now let's learn more about this electric flux, right? So like here the example that I was telling previously, if my area is totally perpendicular to the field lines, maximum field lines will cross. If it is, let's say, tilted like this, these field lines, right, which were previously crossing will not cross now. So they have, the electric field lines crossing has reduced, hence what will happen, the flux will reduce. Here no electric field lines crosses because it is parallel to the electric field lines. The surface is parallel to the electric field lines. So direction of the surface is also very important. So basically what happens, I will take the projection of this, right? I will take the projection that I will see what is the perpendicular component of this surface, and the electric field lines passing due to that perpendicular component will be the total flux. So A perpendicular is magnitude of A cos theta. Okay, and total flux is what? Total flux electric flux in engineering is D, magnitude of D, total electric flux density. Like it tells us the intensity of electric field lines irrespective of the atmosphere, right? Into magnitude of A into cos theta. So electric flux, I can write in simple terms, will be D dot A. So that's how that formula came that I previously explained. So A is the area vector, surface vector, that I have already taught you at the prerequisite chapter. So obviously we'll use it here. Okay. And theta, how much, what is the range of the theta? Theta can obviously 0 degree to 180 degree. Okay. Theta can obviously go from 0 degree to 180 degree. It is theta is the angle between electric area vector. Okay, so it will be the angle. Now like how do you compute flux? Like for a single surface it is fine, but how do you compute flux for multiple surface, for curved surface? So what we do to calculate electric flux through a surface, we divide the surface into multiple small segments and then calculate the overall sum of that. Just same like how we computed electric field intensity, how we computed force, right? Just taken small components of charges, then I added up. So here I will divide each of these components, right, into small areas, and so each of them will produce some electric flux. Okay, due to some small area, D, electric field intensity, will depend on the function, will depend on the position. Due to some small area, AI, okay, flux of the ith surface will be D dot AI. So then what I will do, total electric flux phi, I will just simply add it up because it is a scalar quantity. I can simply add it up. Okay, phi I from 1 to n. Okay, this can be divided, I equals to 1 to n equals to D dot delta AI. Okay, but if it is continuous, if I break these small surfaces to infinitesimally smaller surfaces, right, if I cannot measure them, so it will become continuous. So basically my total flux will be then surface integral, this is the open surface integral of D dot ds. Okay, because ds is very small surface. Okay, so this, so electric flux, I haven't taught you what unit electric flux has. So electric flux basically has units of coulomb. It has units of coulomb. Okay, this is the formula that you should know for any generalized surface. Okay, for not normal surface, because for square, for rectangle, for circle, you will be able to do it. Okay, but for any surface that is not well defined, you have to use this particular formula. Units is coulombs, actually coulombs. Okay, and this is for open surface. For closed surface there is a formula as well that we'll learn. For open surface, this is the formula that you need to use, that flux throughout a surface will be D dot ds throughout this surface S. We have to integrate throughout the surface S for small surfaces, and we'll get back our flux net. And for closed surface, phi net formula will almost be similar, but it will be a closed surface integration, right? Throughout the whole surface it will be D dot ds for closed surface integration. Okay, the formula will just change a bit. It will be for closed surface. Okay, so now let's do a basic question. Okay, like basic common sense question. This, right, you don't need any integration formula, nothing. A point charge Q is positioned at the corner of a square with side length A. So I have a square and a point charge is just positioned here, Q, and its side length is A. Determine the electric flux through the square. Okay, what will be the electric flux through the square? One thing I notice is that the electric field lines produced by this particular cube will be like this. Now, are these field lines ever crossing the surface? So here I can write electric field lines are never crossing the surface. Okay, electric field lines are never crossing the surface. If electric field lines are never crossing the surface, obviously my flux will be simply 0, because like the angle between them is 90, or not 90, sorry, yeah, it is 90, because the area vector is this and electric field lines are something like this. It is never crossing. Area vector and electric field lines are never crossing. Okay, so it is simply 0, because here, right, this is just a sheet. They are never crossing, right? Electric field lines are never crossing. Just it is over this, parallel to this sheet, just like here. This is a sheet, okay, and electric field lines are something like this. Okay, is it crossing? No, right? It is never crossing. It is never crossing. Electric field lines are going here, but it is never crossing. Okay, so electric here, right, flux will be 0. Let's do more examples to get a good grip on this electric flux concept. Now this is a good concept of projection. So this I have taught in double integration. So if you haven't already learned the double integration for me, go and watch the concept of projection. There I have taught how to take the projection of particular surfaces. Calculate the electric flux through the curved surface of a hemisphere of radius r if it is placed in a uniform electric field as shown. So here, right, what you need to do is you need to identify the flux. So what is the formula for flux? Formula for flux is simply E dot ds, not E dot ds, sorry, D dot ds. Okay, throughout the surface. This is the open surface, right? This is not a closed surface. Here electric field is uniform. Okay, electric field is uniform. What is electric field? Electric field is actually, let's assume the directions. Let's assume this as z, x and y. Electric field is in y direction. Okay, E is equal to some constant magnitude Ey minus Ay cap. Okay, so E is in this direction. Now what else we need to do? Actually, if I find out the projected area here, the angle here between the electric field and the area is simply 90. So it will always be constant. Okay, because all this, right, basically if I just place a sun over here, if I just place a sun over here, okay, the projected area of all these small areas, right, this small area will come somewhere around here, this small area will come somewhere around here. So totally cover this circle disk, it will make total disk. So area will be pi r square. This will be disk, area of a disk is pi r square, and the angle here is 90. So as d is constant, I can take it out. Okay, this component will be out, and dot cos theta. Theta is what? Theta here, right? This is in ax cap direction. Okay, this is in minus ay cap direction, and this surface angle is in plus ay cap direction. Okay, so overall I am just I just care about the area. Okay, I just care about the area. So actually what I will do is, this will be, I will tell you, direction will be ay cap, and this direction also I can assume as here and here. I don't care about the magnitude. I just care about the what do you say, I just care about the direction only. So area vector will have its own magnitude. Magnitude is pi r square, right, and direction is, you can choose any a plus minus ay, because mainly I'm concerned about magnitude only right now. So I'll take the magnitude of this right now. So it will be ey, or here they have mentioned e, so I will write here e, okay, into pi r square. obviously I have to divide by epsilon as well, because this is electric flux density and it is electric flux intensity. So this will be divided by epsilon. This will be my flux passing through the surface. So I hope you got the point. This will be equal to d pi r square. Okay, pretty simple, just taking the projection area. If you couldn't understand how this disk formed, you have to go back and watch my double integration video. There I have explained projection a lot. Okay, and here at this point, everything is perpendicular to the electric field lines. All the electric field lines are perpendicular to the surface. So this dot d, this simply is 1. Okay, and this is pi r square. And as I'm concerned about magnitude, I will talk about sign as well later on. I'm concerned about magnitude, so magnitude will be pi r square. The flux will be d pi r square. Let's do it for more examples. Let's do it for this. Again, if electric field lines are here, right? If electric field lines are here, what is the projected area? Again, I can observe that this surface is always perpendicular to the electric field lines. So if I take the projection of this particular areas, right? If I just copy this, this small area, if I just take the projection, it will totally cover this whole rectangle. So basically my flux will be simple. For this type of standard type of shapes, you don't need to use that integration formula. It will be electric field electric flux density into area. So as this is always perpendicular, so that is cos not perpendicular, sorry, perpendicular to the surface, and the surface vector and the electric field are always parallel with each other. So it will be cos 0. Cos 0 is 1. So this will be E is a constant vector field divided by epsilon into, what is this area? This is 2L. This is L, and this is what? This is 2R actually. So this area will be L into 2R. Okay. So next B portion is what? Again, if I take the projected area, now I have to take the projected area along this direction, not this direction, because flux is passing here. So the area is already simple, right? All the flux that will cross, all the field lines that will cross through this particular area will always be perpendicular. Okay, so I don't need to take any concept of projected area. It is already there. Okay, if the angle is different here, right? The angles were different actually. If you observe, the angles were exactly not 90. That's why I had to take the concept of projected area. Okay, so here what will happen? Again, the simple flux formula phi will be simply E divided by epsilon into, what is the area of this? It is pi r square divided by 2, right? Area of a disk is pi r square, so it will be pi r square divided by 2. Okay, so that is the flux that is passing through this particular surface. We'll talk about closed surfaces later on, because flux passing through closed surfaces can be 0 as well. That will talk. So electric flux through open surface, it is used when electric flux field is uniform. The electric flux through open surface is calculated using by the projected area by projecting the electric field onto the surface area, and is given by the expression this. Okay, why I do this? Because this, right, makes the theta 0. If this makes the theta 0, the that projected area if I get the projected area and the angle between the field lines and the surface vector, area surface vector is 0, then this computation becomes simpler. Okay, this becomes very, very simple. So that's why I do this. Simply then we have to do this d dot a cos theta, and theta is 0, so hence d dot a, simple d times a, we get the answer. Okay, so that's how you do this. So you can, like, this can be used as electric field intensity as well. The units will change, then the units will basically change. That's it. Okay, yeah, that's basically it. Just remember one thing, that whenever there is a like a non-standard shape, use the concept of projected area. Okay, and make, so first of all, non-standard shape, standard shape. If given non-standard shape, then use concept of projected area. Okay, that is the first thing. Then what else you have to use? You have to use the concept of the projected area or surface should be perpendicular to the field lines. Now if they are perpendicular to the field lines, the area vector and field lines become parallel. Okay, they simply become parallel, and if they become parallel, then theta becomes 0, computation becomes simple. Okay, computation becomes simpler. Okay, that's why we do this. Let's do this particular question. This will also help you get better understanding of the concept of projected area. So I have this wedge like structure. Okay, just hold on. I have this wedge like structure, right? And electric field lines are just like this. We have to determine the electric flux through each of the 5 surfaces of the inclined plane as shown in the figure. What is the total flux through the closed surface? So this is the homework for you. This I will give you the homework. Okay, what will be the total flux through the surface and the flux through each of the 5 surfaces? Just compute the projected area. Here the electric field lines is already 90 degrees, so the surface A, E, F, D, this, right, is already we don't need to take any projected area here, right? Through this surface A, B, C, D, it is not 90, so we'll take the projected area and then we'll actually find out the total flux. Okay, so you try to do this. This is the homework for you. Again, this question: calculate the electric flux through the curved surface of a hemisphere of radius r if it is placed in uniform electric field. So here also we have to find out the projected area. So I am not solving it in front of you. Again, you have to find, like here the angle is not directly 90 with respect to the surface, so you have to find the projected area and solve for this question. This question is the same question. Okay, all of these are same concept only, and this as well same question. So I'll give all of this homework, and in the next lecture we'll learn about all of this. Okay, so now we'll learn about Gauss law. What is Gauss law? Gauss law relates the electric flux through a closed surface, Gaussian surface, to the charge enclosed within that surface. So it is a law. So Gauss has defined a law that, just hold on a second, that my this surface integral, right, that is flux. This is also known as d net dot ds, or also known as flux, through a closed integration of d net dot ds, that is the flux through a closed surface, will always be equals to q enclosed. Enclosed means the charge that is enclosed within the surface. So let's say I have a q1 charge over here, q2 charge over here, and minus q3 charge. So this q enclosed will be q1 plus q2 minus q3, and that will be basically equals to my flux. I don't need to do all this. Right? No need to compute. The flux, overall flux throughout this surface, throughout this closed surface, will be phi. So it always mentions about closed surface. So this you have to identify. Only for Gauss's law is only valid for closed surface. So we don't need to do any calculations. Things become so simple. Okay, just q enclosed you have to identify, and that's it. I don't need to do anything. Now also this law, like this flux, right, this flux is due to any electric field, right? If due to all the charges, so I don't care whatever charges are outside. Okay, due to all charges present inside or outside. Okay, so due to all charges present inside or outside, let us understand why is this the case intuitively. So if a charge is present here, right, q, whatever the amount of flux that goes into the surface, the same flux actually goes out. None of it is stored in the surface, right? None of it is stored in the surface. Okay, so whatever comes in goes out. Okay, for any outside charge, but for inside charge, this creates a flux, but this crosses here once only, not twice. It doesn't cross the surface twice. This field line doesn't cross the surface twice. This field line crosses the surface here, surface 1 and surface 2. So it comes in and goes out. So comes in and goes out. So zero flux total inside. But due to this charge, there is some flux. Okay. So that's why I don't care about outside charges. I only care about the inside charges. Just hold on. Yeah, this is fine. Just let me do this thing. Yeah. I only take care of the inside charges, not take care of the outside charges. So Gauss's law is the net outward electric flux through a closed surface that forms a volume. Okay, it's a hollow surface or a solid surface, I don't care. It should form a volume, is equals to the algebraic sum of the charges enclosed within the surface. Inside the surface, whatever the charges are, if I do the algebraic sum, I will get the total flux. Simple as. Okay, so double integration of closed surface integration of electric flux density dot ds will be equals to q enclosed. If I have point charge, this is a point charge form. If I have line charge, I will simply integrate the line charge and I will find the total charge. Remember, right? We did a sum, we did a numerical how to find the total charge. I will simply integrate the line charge. If it is a surface charge, I will integrate the surface charge. If it is a volume charge, I will simply integrate the volume charge. Okay, with respect to volume. So I hope these are the different formats of Gauss's law. So it helps me to find the flux throughout the surface. It becomes so much simpler. Okay, so I hope you understand that whatever charge amount of charge present inside the surface there is, it will be equals to the sum, algebraic sum. Okay, that will be equals to the total flux present. Okay, so the flux actually only depends on the charges present inside and not outside. As if some charge is present here, it will cross this surface and then again it will come out of the surface. But if some charge is present inside, it will cross the surface only once. One electric field line will only cross the surface only once. So that's fine. Okay, so here I have tried to explain. Let's take this particular charge, right? If this charge is there, so this is a hollow sphere, this is also a hollow sphere. So electric field lines crosses through this surface only once. Here also I observe electric field line is crossing through this surface only once, but here the same electric field line is crossing here and here. So the net coming in and net outward is equal. So the flux due to this particular electric field line is zero. So I don't care about the outside electric field lines or outside charges. I only care about the charges inside. Okay, so flux of phi s2 will be simply 0, as electric field lines as incoming is equals to outgoing. Okay, but here in the surface S1, phi S1 will not be equals to 0. Phi S1 will not be equals to 0. The electric field on a surface is due to both internal and external charges, but flux is only due to internal charges, as mentioned multiple times. So let's take another example. Here I have a plus q charge, right? Now if I break this down into two surfaces, what will happen? Now the important, like this is, let's say what you do is, actually sometimes the surface is not present. Where is Gauss law used? We use Gauss law to actually find the electric field intensity, that I will derive later on. Okay, so it is very useful to use that Gauss law. We need the concept of Gaussian surface. So what is a Gaussian surface? To calculate the electric flux for a point charge, we often choose a spherical Gaussian surface centered around the charge. So we actually choose Gaussian surfaces according to our own needs, according to the charge distribution that is present. I'll choose it later on, you will see that. Okay, so we choose according to our own use case, which will be easier for us, so which will actually follow the Gaussian symmetry. Once we select the surface, you will understand. This surface, Gaussian surface, is selected because the electric field is radial and parallel to the differential area vector. So as electric field will be radial to the surface and it will be parallel to the differential area vector, so again that computation of electric flux will become simpler. So that's why we choose Gaussian surface, like here in this case sphere, because it is radial for this point charge, right? Electric field lines and the surface vector direction will be parallel to each other. So that's why Gaussian surface for a point charge is sphere. For other charge distributions, we'll choose accordingly. Okay, so that was one concept. So another concept is that if, let's say one thing, if I have placed a point charge here, Q, and this is a perfect conductor. Okay, this is a perfect conductor, perfect conductor. So what will happen if this is a perfect conductor, right? If this is a point charge Q, what will happen is that whatever charges I had here, those will actually be on the surface here. Okay, because this Q will actually generate a electric field which will be radially outwards. Okay, and what will happen due to this plus Q, all the, like, this is not a conductor, this surface S2 is not a conductor, surface S1 is a conductor, S1, okay. So this will be simply here plus all the charges will be here coming, because all the positive charges will be forced in this direction, right? So all the positive charges will be gathered here, and all the negative charges will be gathered somewhere around here, right? Because positive charges, like, they cannot, like, let's say they cannot escape out of this, so all the positive charges will be repelled and the negative charges will be somewhere around here, right? Because negative charges will be attracted with the positive charges. So if you observe, like, if you use the same formula, right? If you use the same formula, that here actually what will happen, the flux, the electric field here is 0. So overall, in this particular region, right, this will generate total plus minus Q of charge. Okay, and this will generate total plus Q of charge. Why this will generate minus Q of charge? Because I know the concept of electric field intensity inside conductor. Electric field inside a conductor is 0. If electric field is 0, hence the flux will also be 0, because no flux is crossing the surface. So in this phi S1 will be 0. If phi S1 is 0, it is basically the sum of the charge enclosed. So this charge is Q. Let me name this charge as Qx, and let me name this charge as Qy. Okay, why am I doing this? I will explain you. So here this will be equals to what? This will be Q plus Qx. Now this is equals to 0, so my Qx will be equals to minus Q, and exactly I have just done that same thing only. All the negative charges will be attracted to the positive charge here, but it cannot go inside the conductor because it is a perfect conductor, and inside the conductor there is no charge. I mean, somehow this charge is there, but there is no field. Okay, so that is one thing. What about phi S2? Now phi S2, right? What happens? Phi S2 actually is due to this negative, because here there is no electric field. Here there is no electric field. Electric field is only present on these surfaces. Okay, so what happens is phi S2 is what? Phi S2 is summation of all the charges again. So it is simply equals to Q. So it is equals to Q plus Qx and plus Qy. Now this is 0, so this Qy has to be equals to what? Total charge enclosed in this particular thing. Okay, or total flux. The total flux due to this is Q only, right? Plus Q only. That is what we will get, because here I have generated minus Q of charge. This was initially neutral, so it has to be neutral, right? It has to be neutral initially. So if it has to be neutral, I know Qy plus Qx has to be 0, because overall this particular object, right, this S2 object was neutral. So Qy plus Qx will be equals to 0. So Qy will be equals to minus Qx. So Qy will be equals to simply plus Q. So overall flux will be plus Q on the surface S2. Okay, so this, don't worry if you couldn't understand it right now, we'll use this example later on as well, so we'll understand this. Okay, so main point what I wanted to talk is, if there is some point charge inside, like S1 is a perfect conductor, if S1 is a perfect conductor, and if there is some point charge, somehow I get it here. So due to this point charge, actually by induction without any touching, it will generate negative charges here of magnitude what? Of q again, but it will be minus q. It will be minus q. Okay, and this will be again, this will generate plus q. So overall the arrangement will be something like this. The flux in this S2 surface will not be 0. Flux in S1 surface will be obviously 0, because there is no electric field lines. Okay, electric field inside the S1. Okay, electric field inside the S1 is equals to 0. Okay, so that's about it. And Gaussian surface, like what type of Gaussian surface we choose, I will talk about that. The Gaussian surface is hollow, spherical, centered around the point charge. For a point charge, it is hollow spherical surface. The Gaussian surface is a hollow cylinder with the line charge running along its axis. So if I have a line charge like this, okay, so how will the electric field lines be? Electric field lines will be like this, right, radially outwards. Okay, if I choose a cylinder, isn't that suitable? If I choose a hollow cylinder, can you tell me, will it be always perpendicular to the surface? Here it will always be perpendicular, right? It will always be perpendicular, radially outwards, it will always be perpendicular. So that's why I choose a hollow cylinder. For a sheet charge, the Gaussian surface is often chosen as a cuboid or cylinder with top and bottom surfaces enclosing the sheet. So sheet charge, again, if I choose a cuboid, it will just be perpendicular. Okay, for a spherical charge distribution, the Gaussian surface is also spherical. If it is spherical, just like point charge or any other spherical like ring or anything, we'll choose spherical charge distribution. Now let's do few questions on this Gauss's law. Two hollow concentric spheres are present, okay, S1 and S2. So this is S1, this is a hollow sphere, and this is another hollow sphere. They are concentric, that is they have same center. Enclose the charges Q and 2Q. So S1 encloses Q, S2 encloses 2Q. What is the electric flux through S1 and S2? So what will be the electric flux through S1? Can you do this for me? I will simply use the Gauss's law. They have not mentioned anything about conductor, so I will assume that this is not a conductor case. This is just normal generalized case. What have we learned till now? The electric flux, okay, is basically charge enclosed. Electric flux is basically charge enclosed. One thing I forgot there, it was Q by R. So this thing is correct. It was coulomb per, yeah. Electric flux is summation of charge enclosed according to Gauss law. So my phi S1 will be charge enclosed is what? Is plus Q. Okay, charge enclosed is plus Q. What about this? Is the flux. That's it, right? That's how simple it is. That's how simple it is. Okay, now actually one thing is, we have two identities. If this is according to the D quantity, okay, if they are asking, like, they will mention the units. I will talk about okay, electric flux. I will say find flux both in coulomb and voltmeter. Okay, so in coulomb this will be Q only, but in voltmeter, so this is one of the definition, this is other definition, that is Q enclosed, okay, divided by epsilon. Actually I forgot to write that point of time. If I want to define it in terms of electric field intensity, right? If I want to define it in terms of electric field intensity, this, right, flux, electric flux can also be defined as Q enclosed by epsilon. This unit is this is in electric, like this is in terms of electric field intensity, and that was in electric flux density. So this has charge, this has units of coulombs, and this is units of voltmeter. Okay, just have to take a note of this. This is units of voltmeter. Okay, so yeah, that's pretty much it that I wanted to say. This is also another unit of flux. So here epsilon they haven't mentioned. So what is the ratio of electric flux through S1 and S2? It doesn't matter, right? It doesn't matter because ratio anyways, epsilon will get cancelled. So this is phi S1, okay, and phi S2 is what? Phi S2 is this Q plus 2Q, because total charge enclosed is in this whole Gaussian surface, right? If I take a Gaussian surface here, this is a sphere, right? Gaussian surface is a sphere, so it will be 3Q. So it will be 3Q coulombs. So what have they asked? Ratio between S1 and S2. So S1 S2 is Q upon 3Q, so it will be 1/3. Okay, so now that is the case of 1/3. Now if the B part, what is the B part? How will the electric flux through surface S1 change if a medium with a dielectric constant of 5 is introduced inside S1? Okay, replacing here. So previously I assumed that this was epsilon naught only, but now replacing here a dielectric constant of 5 has been placed. Okay, so if that has been the case, so my flux phi E, right, will be Q upon epsilon, that is Q upon epsilon naught into epsilon R, that is 5. So Q upon 5 epsilon naught. So here it was previously, it was Q upon epsilon naught only, because epsilon R was 1, it was air. So flux will become 1/5 of the previous case. So we'll simply write will become 1/5 of the previous case. Okay, so that is a thing that you need to understand if I replace it with here. So this is a question: a cube of side length L, so I'll write this in proper capitals, has one end at the origin and extends along positive x and y axis, x, y and z axis. Okay, y and z axis is okay. Cube of side length L has one corner at the origin and extends along positive. Okay, it is like a cube of infinite length. Fine. So one end is corner and other end are obviously extending. Okay, they are extending actually. Just roughly making it, they're extending. So what are they asking? The electric field in this region is E. Okay, in this region is E here. The charge enclosed in the cube length L. Okay, sorry about that. Actually, this right, this extending in the positive. Okay, they're extending the positive x and y. No, not infinity. Sorry, it has length L, right? So all of it will be L actually. Sorry for that. All of it will be L simply. So what are they asking? They are asking the charge enclosed inside the cube. How do I find out the charge enclosed inside the cube? So what I know, this basic formula, that Q enclosed is integration, closed line integration of D dot ds. And if I want to convert it into electric field, this will be epsilon E dot ds. Okay, this will be my Q enclosed. Now can you solve this from here? Can you solve this from here? Just have to integrate this E over the whole surface. Now this is a variable, this is not constant. Okay, so just be careful about solving the integration. Integration is pretty simple, you will be able to solve it. I have hope on you. So just this is also the homework for you, and in the next lecture we'll solve all the assignment problems, because there are so many problems here. We'll solve all of them. Okay, next is Gauss's law in point or differential format. Okay, so basically if I have a Gauss law in the volumetric format, right, if it is a volume integration, then I can do what? If a volume charge density rho v is present inside a volume v, Gauss's law is in its Gauss law in its point form is expressed as this. So this obviously I have explained previously as well. This actually I can use a divergence form, right? What is divergence form? If computing this is difficult for me, computing surface integration is difficult for me, we have studied from vector calculus that if this is a closed surface, I can simply write del dot v dv. Okay, this is the Gauss divergence formula. If you remember, this was the Gauss divergence theorem. So if this is more easier, we can compute this. Okay, this should be equals to the volume integration of rho v dv. Now what relation I get? I get this relation, that the point format, that del dot v should be equals to rho v. This is a very important relation that we should know, that del dot v will be equals to my rho v. Okay, rho v is what? D is the electric flux density, rho v is the volume charge density in coulomb per meter cube. Okay, so that's the unit. So one thing you have to understand, that to use this particular thing, right, your very important D, that is electric flux density, must be continuous and differentiable. So these two things you have to take care. D must be continuous and differentiable, then only you will be able to see, only then this relationship is valid. So you have to identify if this is valid relationship or not. This can go invalid as well. So we can use this formula, okay, for solving our questions. So let's do one question on this. Okay, so we have a question: for a given configuration, the electric flux density in vacuum is given as this. The charge present inside the cylinder, rho equals to 1 from z minus 2 to plus 2. So how do I know the charge present? Let's solve the first part, then I will solve the second part. Okay, then in the second part I have to find out the volume charge density rho v. Okay, so how do I find out the charge present? Q enclosed will be what? Q enclosed, we know formula for the first part, right? For the first part, Q enclosed will be equals to integration. This is a closed surface integration, right? Because this is a cylinder. Okay, cylinder. This is present inside a cylinder, so cylinder is a closed surface integration. Closed surface integration d dot ds. Correct. Now integrating this, right, may be a bit difficult, because this has z rho cos square phi. It may be a bit difficult for me. So what I can do, I can convert this into easier format. So if you like, homework for you is method 1 is directly solve using this d dot ds, right? Because here the ds vector will be different at different places. I'll show you what do I mean by that. Z x y from z equals to plus 5 to minus 5 and rho of 1. So here I observe the ds vector. This is one ds vector, this is another ds vector. Okay, this is another ds vector, this is another ds vector. So ds vector is varying, so computing this is difficult. So what I will use, I will do this. You can do this. You can break this down into different surfaces and then compute the integration. I will use the Gauss divergence theorem. But for that, you have to identify whether this is continuous and differentiable. Yes, this is continuous and differentiable because this is just a simple polynomial. There is no denominator. Okay. So what I will do, I will use this formula, volume integration of del dot d dv. Okay. Now, do you understand why in basics I taught you how to find the divergence in other coordinate system? Now we'll use this. Now basically we'll use this. What is del dot v? Just write the dl now. How to remember? Just write the dl. And from there you will remember the h1, h2, h3. dl is what? For first it is d rho a rho cap. Next it is what? Plus rho d phi a phi cap plus this will be simply dz az cap, right? So if you remember, it was h1, h2, h3 whole divided, so this will be 1 by rho only, and first I have to differentiate with respect to the other two, multiplied by the other two, that is rho. So this will be, I will just write it here, dd rho. Now that's how you recall, right? It's been a distant past since we learned this. Rho into this particular thing, z rho cos square phi. Z rho cos square phi. Plus dd phi what is it? It is basically the other two, right? It will be simply 1 times again the same thing only. Okay, in which direction is it? Okay, it is in az direction only. Okay, it is in az direction. Why am I doing all this? We don't need to do all this, right? It is in az direction only. Okay, if it was in az direction, actually the d, like this dot product would have been bit simple, but still, so if it is only in this direction, right? So these components will not matter to us, only this one will matter. ddz, this will be rho again, and this will be z rho cos square phi. Okay, that will be the only divergence. If you are not able to recall, go back and watch the basics video, right? So here what will happen, rho will be here, so there will be rho cos square phi. So this will be basically the simple del dot v. Now I can simply do this integration, right? So my flux, or what are the charge present inside the cylinder, right? So q enclosed will be simply triple integration rho cos square phi d, this will be dv will be changed to what? Rho d phi dz, if you remember, right? So rho will go from 0 to 1 because radius 1 they have told me. Phi totally, the cylinder I will cover total 2 pi, 0 to 2 pi, and z will go from -5 to +5. Okay, this will be the limits. So they are all in multiplication format, so I can solve them individually actually. So how will I solve them individually? So this, right, this I will get here. So charge enclosed will be simply, this will be rho q pi 3. If I solve this individually, cos square phi. Okay, cos square integration is a bit difficult, we have to do this. So cos square phi from 0 to 2 pi, and this one will be basically z from -5 to 5. Okay, so what will be the integration of cos square phi? You can convert this into single angle formula as well. If you remember, it will be so cos square phi minus sin square phi is, like, if you ever tend to forget, right, you can write it like this: cos square phi minus sin square phi is cos 2 phi. So cos square phi, I will break the sin square phi to 1 minus cos square phi, so this will become 2 cos square phi 1 minus 1, it will go 1 plus cos 2 phi divided by 2. So what will happen is that if I integrate this whole thing, right, if I integrate this whole thing from 0 to 2 pi, this will be 0, only this one will be left. So 1 by 2 pi into 2 pi, that is pi. 1 by 2 into 2 pi is simply pi. Okay, so this one will be 1 by 3 into pi into 10, right? So yeah, this is what I will get basically. So z is it correct? From z equals to okay, sorry, it was from z equals to minus 2 to plus 2. Sorry, my mistake, the limits are wrong. It should be minus 2 to plus 2. We can do it for minus like we can do it for minus 5 to plus 5 as well. Doesn't matter, right? Doesn't matter. Okay, so this will come out to be 10 pi by 3 coulombs. This will be the answer to this question. This is a very, very good question. Okay, now you have to obviously see, is this like, for you to apply this, right? For you to apply this, you have to see that what is d is equals to z rho cos square phi az. So you have to see that is it analytic or not. So it is analytic. Okay, how it is analytic? It is just simply polynomial, right? Polynomial, and cos is there, so it will be analytic. None of where at any point you put x equals like z rho phi, it will not break, it will not be infinity or identified, right? It is analytic. Okay, so that was the case here. Let's find out the volume charge density. How do you find out the volume charge density? Simply the volume charge density is nothing, right? Volume charge density, I just taught you the formula. Volume charge density is simply del dot d, right? So we have computed the del dot d. What is it? It is this, right? It is simply this rho cos square phi. So this question would have been even better if I would have asked you to find volume charge density at point p equals to 1 2 3. Okay, they can ask this, not to p equals to 1 2 3. Sorry, yeah, we can do p equals to 1 2 3 as well. So if this is in simple Cartesian coordinate system, right? This is in simple Cartesian coordinate system. So then what you have to do, first of all, you have to convert this p 1 2 3 into cylindrical. This is in Cartesian. You have to convert this into cylindrical. So this type of question can come. So if you want to convert this into cylindrical, what you have to do? So your x and y component is this. So what is your basically rho? Rho will be under root x square plus y square, if you remember. So it is under root 5. Okay. What is your phi? Phi will be tan inverse y upon x. So if I just compute this very quickly, just hold on. 2.1 where is 1 tan inverse, so it will be 63.44. if I want to convert this into radians, right, to tan inverse, it will be 1.1 radians. Okay, and your z will be z, that is 3 itself. So in cylindrical, this will be under root 5, this will be 63.44 degrees, and this will be 3. Okay, so here this I should mention, this is in Cartesian. Okay, so now what you will do, you will put the values, right? You will put rho v at point P equals to this, right? This particular thing will be equals to this rho is under root 5 cos square 5. So if I take the cos of this and if I square it into 5 under root, it will give me almost 0.447 charge per meter cube. So this will be the answer. It doesn't matter what z is because it is independent of z. Okay, I hope you understood this question. This question is a very good question, and this type of question can obviously come in the examination. Haven't came yet, but this can come actually. Okay, so this question I will give you as homework. Same question, same concept. Okay, in vacuum we have to find out the volume charge density and charge present inside the closed surface. Same concept. Okay, just use the same concept here. Again, this is analytic, right? This is analytic. I can observe this is polynomial. If this is polynomial, it has to be analytic. If you haven't studied complex variables for me, you have to study if you want to understand what is analyticity means. Okay, this one is also homework for you. And that's it basically for this lecture. And in the next lecture, we'll mainly solve the assignment questions that were remaining, and the we'll see if I am able to start a new topic, or I will totally give the next lecture as homework question solution, and after that lecture we'll start the new lecture. Okay, thank you for watching. I will see you in the next lecture.